This is my friend Srinivasan, who is going to tell us about bringing message passing concurrency to Java. If you don't care about Java and have never had trouble with locks or threads, maybe you're not in the right audience. I think I'm safe in assuming that you all have.
Thanks, Anu. Just as a brief note, some of the techniques that I'm going to be talking about are, I'm sure, equally applicable to other imperative languages with pointers. So although it says Java, the framework that I've developed is for Java, but many of the techniques are still more globally applicable. And so I was working with Anu and for the longest time in industry, developing high-speed, high-performance transactional frameworks. And the last thing that we did was write the WebLogic application server together. And in all the pieces of software that we developed, we ran into concurrency issues, whether it is device drivers or app middleware, you run into concurrency issues. And there were a bunch of problems that I wanted to tackle. I keep running into these over and over again. So as a background, as we all know, processing is getting increasingly distributed. Multiple cores per box, multiple CPUs per box, multiple boxes, multiple data centers. So a programmer not only has to worry about distribution at a micro scale, it's distribution at a macro scale as well. And everything is distributed. There is one characteristic that concurrency solutions don't really deal with, which is isolation. Meaning they deal with it, but it's not given enough respect. And more often than not, you run into these issues where you need something to be tested and run in isolation. And if you have a lock-based system or a shared memory-based system, it's really not isolated. It's not testable in isolation. So to me, that's a prime characteristic. And current problems with concurrent solutions are how to get safety along with speed. You have to worry as a programmer about memory models and consistency and double-check locking and all kinds of things, where to use volatile, when not to use volatile, stuff like that. And of course, the problems with shared memory concurrency are well known. And one of the things that is important is incorporating external actions. So for the most part, when you look at concurrency solutions, all the examples that you'll see, they have to do with manipulating data structures, put a synchronized block, or how to deal with multiple producer consumers or red-black trees or whatever, if you look at examples. But the moment you put in an I/O action, everything changes, because the understanding is that you don't take a lock and then wait for a file I/O to complete. And the moment you have external actions, the solutions are very different. And that's where all the bugs come in. It's very easy to get a data structure manipulation right. But the moment you have to interleave all kinds of external actions, you will get it wrong. And that's where, because you're increasing what you thought was originally atomic, you have to break it down into several sub-tasks, which involve I/O interleaving. And that interleaving essentially gives you all kinds of problems with the original intention of atomicity of the entire task that you had originally intended. And the final sort of background for this is that I see server applications as staged data flow networks. And this whole staging data flow thing is coming back in a big way in other areas as well. If you look at graphics, using graphic cards for embarrassingly parallel computation, this meme is sort of coming back. So there are lots of things feeding into why I went with Kilim and message passing as a more fundamental construct than using shared memory. So I tend to see message passing everywhere now, and it's not new. I mean, this has been there since Tony Hoare talked about communicating sequential processes. So message passing everywhere and shared nothing. So this is a Erlang idiom. And if you will, this is my ode to Erlang. So shared nothing is equivalent to failure isolation, right? If you don't share, it's good. It is easy to reason about and debug. It's easy to reason about. That's the reason why, if you look at any process calculi, whether it's CSP or PyCalculus or any of the process calculi, they are all process and message oriented. And there is no reason why you need to have two different mindsets. one to reason about and one to develop with. So if any of you have done model checking with Spin or Promula, you have this message passing view of the world, and then you transfer it to the shared memory view of the world, and there's a huge disconnect between the two. And I would like to eliminate that distinction. Likewise with concurrent and distributed programming, there are two different mindsets. One, you do local shared memory thread-based programming, and then you do distributed stuff. There are two different mindsets, and a lot of it doesn't need to be that way. And to me, sending a message to disk is just as asynchronous. It takes a little bit of time before it comes back as a remote computation. So I would like to see a unified view of both concurrent and distributed programming. So message passing neatly fits a bill. But in order for message passing to succeed, you also need lightweight threads, which is one of the reasons why it's not taken off, I believe, which I'll cover soon. And the features that I like about having very lightweight threads, first of all, because it's a thread, you have automatic stack management. So you can have A, B, C, you can call, and you can write it sequentially and let the system worry about managing the stack. And the second part is that if you have extremely lightweight threads, and I'm talking about having the possibility of having millions of these little lightweight things on a humble laptop, then you can easily map it directly to user-level concurrent tasks. So in your case, if you have a HTTP request come in, that can be broken down into lots of subtasks, like parsing, negotiation with security, lots of stages there. And there are some stages that are very short-lived, so parsing will be a very short-lived thing. But if it involves security negotiation of any sort, that becomes a slightly more longer-lived task. And the idea is to be able to spin off these tasks without thinking about it. Right now, if you have just kernel threads, you do think about it. It's heavyweight, so you tend to form thread pools, all that kind of stuff. And you should not have to think that way at all. So that's a background. And I believe that one of the reasons why message passing, or some of the reasons why message passing has not really taken off, and you can correct me if I'm wrong, is that the general meme is that asynchronous programming is hard, and that's probably because most successful languages don't deal with asynchronous programming very well. You have callback-based programming, basically, which tends to be verbose and control gets inverted. So if you have something that's written with callbacks, it's difficult to figure out what the flow of control is. The other problem is threads have traditionally been very heavyweight. So you don't think in terms of having tasks and or threads and message passing between threads. So for more often than not, you'll see this message passing as a meme. In fact, if you search for message passing, you will almost always land up with MPI, because those are the kinds of tasks where the computation takes a whole lot of time. And so having a heavyweight process sending a big heavyweight message is really not an issue. But it really, message passing at the micro level has really not taken hold. And the third part, I believe, the reason why message passing has not taken hold is that it's seen to be expensive. In order to guarantee safety, in order to guarantee interference freedom, you need to copy a message, right? Or you have immutable messages. And context switching also is expensive. So essentially, these are the reasons I believe that message passing has not taken off. And I have addressed these issues in this framework called Kilim. Kilim is the name that's used for Turkish rugs. It's used in all over Eastern Europe also. So it's a flat weave rug with fine threads and very flexible. So hopefully you'll see the analogy. So ultra lightweight threads, message passing is central. And I'll qualify what I mean by lightweight. Like they say, beauty lies in the eye of the beer holder, right? Messages are, this is a distinction. Messages are distinct from objects. So there are objects, Java objects within a threads, ultra lightweight threads space. And then the unit of currency that's actually transferred across is a message that is philosophically different from objects. And it's not just philosophically different, I enforce that philosophy. So one of the things that I enforce is, or two things that I enforce is no internal aliasing, which means that a node may not have more than one incoming heap pointer. So I don't care about local variable aliases. I do care about pointer aliases. So a node or an object within a message tree or message graph, I guess, doesn't have more than one incoming pointer, which basically means that it's forced to be tree shaped, because at most one pointer incoming, which means it is forced to be tree shaped. So that means that there's at most one path leading from the root to any node. And it may sound restrictive at first, but in practice it's turned out not to be very restrictive, because most event-based systems, you look at the X server, or you look at most event-based systems, you look at Erlang, messages actually tend to be simple. And one of the reasons is that when you look at failure isolation as a way of life, you tend to make things simple and open. The interfaces are very simple and open. And so I've merely enforced that observation. And once you enforced something to be tree structured, it gives you very nice inductive properties. And the second part is linear ownership transfer, which is if task A sends a message to task B, task A completely loses visibility of that message. So it's exactly like saying free in C, where once you have handed over the pointer, you don't own it. So semantically, it is a dialect of Java. Syntactically, it is Java, but semantically, there is this additional constraint that's been placed, which says, if you're sending a message, then you lose visibility once you've sent it. So if you want to send a mutable message to multiple recipients, then the onus is on you to make a copy. By default, I do not make a copy, but I lose ownership. So essentially, that means safe and zero copy message passing. Right? You can have a mutable message that belongs only to one space, and it's logically transferred over to another space, and the original sender does not get to see it at all. And the final thing that this package has, in fact, in addition to this, it has a code generator as well, which will create this, which will CPS transform and create lightweight threads, is a runtime library which contains a scheduler. You can write your own user-level scheduler. It has typed mailboxes. And unlike many like CSP-based frameworks or whatever, I don't have the mailbox as a first-class primitive. You can create your own concurrency primitives like futures or mvars or whatever, and take advantage of the type system. And of course, timers and stuff like that. Anyway. So I just want to give you a brief overview of the programming model. A Kilim task is very much like a thread. The programming model looks exactly like a thread, where in this case, it's a HTTP connection, which extends a task. So it's a task per connection model. So instead of extends thread, I say extends task. Instead of public void run, I say public void execute. And after that, I have this annotation called pausable. Pausable tells the code generator that this may pause. Essentially, that means that somewhere deep down, it may call another method that may pause. And the built-in pausable methods are sleep and yield. Okay? So pausable is in some sense like a checked exception, where if a method calls another pausable method, it too must be declared pausable. Okay? So this is to pinpoint those methods that need to be transformed by the code generator. Okay? The eventual transformation is very much like what you would write by hand, which is the return to main loop mentality. But you can write it in sequential form, and you don't have to worry about it. It does all the capturing the closure, ripping the stack. All that stuff is done automatically, and rescheduling it at appropriate time. All that stuff is done for you, right? So you write it in thread-like automatically stack managed form. So in this case, you have a while loop, right? It doesn't have to exit the loop. So you write it as if you're writing a thread. And if somebody calls, like in this case, if it says wait for socket, then until it gets the next message, this will be swapped out, and some other task will be executed. Okay. So that was the task part. And between tasks, the mechanism right now is a simple mailbox, which is just like a queue, which is a queue basically, with multiple producers and a single consumer. And it's typed. So you can say, in this case, it's in a loop which says mailbox.get, process the message, out mailbox.put. And as you can see, this execute is possible. And in this case, it needs to be possible because get is possible and put is possible. Get is possible because it will pause until it gets a message. And put is possible because it will pause if the buffer is full. You have a question?
Is there anything that enforces the multiple producer single consumer instead, or is it just the definition of
Good question. So the question is there any convention that, is there anything that enforces the multiple producer single consumer? Not at compile time. At runtime, yes. So if more than one task waits on the same mailbox, if say it's mailbox.get and they happen to be concurrently waiting for it, one of them will get an exception.
And all mailboxes are?
Yes. All mailboxes are multiple producers and single consumer, but I'm working on different flavors, including synchronous mailboxes, including MVARs, including multiple producers, multiple consumers, that kind of stuff, building on top of it. But as far as I'm concerned, this is merely a library. It's not sort of baked in to the semantics of it.
Oh, okay.
Yeah, that's the difference between CSP and the scheme. Where mailboxes just happens to be one facility, you can roll your own. And finally, the code generator, which I call, we're pushing the Kilim analogy a bit much, is called weaving, which takes a class and transforms it and dumps it into a directory of your choice, or you can supply it an entire directory of classes, and whichever classes happens to contain possible code will get transformed and dumped into the destination. You can overwrite the source directory as well. And the weaver will preserve or will correctly adjust for all the debug information so that you can debug the stuff in Eclipse. Okay, so I'm going to take a look at some of the transformation and the messaging part. So this is a fairly straightforward transformation. I looked at continuation passing style transformations, and they really don't apply very well to JVM-based languages because they don't have tail call optimization support. So, but it's equivalent. And these are one-shot continuations, so it's sort of like coroutines. So the scheme is fairly simple. So if I have a method like this, foo, and let's say bar happens to be a possible method as well, and print is not. Print is just system.out.println. So bar needs to pause for whatever reason, right? What essentially happens is that if it needs to pause, let's say bar calls sleep. What happens is that it triggers a stack unrolling. So it informs, sleep informs bar, bar informs its caller foo, saying, I need to unroll the stack. So save whatever state you need for resumption and return. So bar calls sleep. Sleep at some point will essentially say return to bar. Bar will recognize that, oh, sleep is not done yet. It will return. Foo will need to check, oh, bar needs to return, but it's not fully done yet. It will package I and O because that's the thing it needs to use. Those are the two variables it needs after bar. And it will squirrel whatever state it needs. So every activation frame, as the stack is popping, every activation frame squirrels away whatever state it needs and returns. Okay? And clearly, one of the ways to do it is all the stuff in yellow is the code that I inject. And there's some bit of code at the top and some bit of code around every possible method. So the first part is that there is an extra parameter added to all possible methods. So like with bar as with foo, there's a fiber that's attached. A fiber is essentially an object that threads through the call stack. And so anything that you need to squirrel away, you attach to this fiber. So every activation frame, as it's popping, it attaches stuff to the fiber and pops. And so the fiber is the continuation. It keeps track of the entire control and data plane that's needed to resume, right? So when bar returns, F is the out-of-band information, which is checked to see whether it's returning prematurely or whether it's done. So if it says it's returning prematurely, that means it's pausing. Then this activation frame needs to squirrel away the label to which it needs to jump to when resuming the PC, and I and O, which it needs after resuming. That's a state in this activation frame that's of interest. It will store this and return. Foo's caller will do the same thing, and so on. The stack collapses, and the scheduler will resume the next fiber. Right? So it's exactly what you would do in a state machine if you were to write it on your own. All the stuff that is necessary for you to squirrel away, you have to manually do it and do a return to the main loop. This does it automatically. Question?
How do you make that work for non-void functions?
I'm sorry?
How do you make that work for non-void functions? What's the default return value?
How do you make it work for non-void functions? What's the default for the return value? So let's say if it is an integer, I can return any dummy value. It's never checked. So anywhere where there's a dummy value, I can return whatever is the default for ints or booleans or pointers, right? So coming back to that, when resuming, so again, the whole stack is built up. The scheduler will call execute will call foo will call bar, and the way it does it is that essentially the way it sets up the stack is inside foo, it says it does a computed go to f.pc, jumps directly to L1, bar will directly jump to where it left off, and so on, all the way. And it will say, if it needs restoring, restore the stack, the activation frame that it needs, and continue from where it left off. So there is local surgery around every possible call, which essentially restores all the local variables and the operand stack at that point. So there are lots of details I'm not talking about. For example, you can't just shamelessly jump into into a loop. You can't say go to some place, because the JVM definitely checks whether the stack is balanced, whether the types are right. So I need to pad all the local variables and the stack with dummy values in order to get the types to check. So I do a fairly detailed data flow analysis. Also make sure that duplicates are weeded out. Even if two variables happen to have the same value, then I don't unnecessarily squirrel away both. I just have an instruction with just a dupe of that, stuff like that. So there's lots of constant propagation. All that stuff is done automatically. But you would think that, popping all of this stack and restoring all of it is quite expensive. It's actually not really expensive in the default case if it never pauses, because it essentially involves 2 extra checks. But other than that, nothing really happens. So it's pretty much at standard speeds. It doesn't take much of a hit. But if it does pause, then of course you get something for that, some convenience for what it provides. So you would think that all this stack ripping will be slow. Turns out it's plenty fast. And the term concurrency-oriented programming has been sort of appropriated by Erlang. And so I thought it would be good to check against Erlang. So here's a micro benchmark which takes, say, a ring of tasks, and not a ring. Actually, there are n tasks, each sending a message to everybody else. So n-1 messages, n-1 responses, and a final message saying I'm done. So there's some n-squared messages here. So 3,000 tasks, 9 million messages in about less than 4 seconds. So that's about 0.45 microseconds per message, which including the context switch. Right? Actually, the context switch is the only thing. So you're unrolling the stack and rolling the stack for somebody else, and all the time it's actually quite fast. And Erlang, which is also not too shabby in the scheme of things, it's plenty fast. It's 1.4 microseconds. But you can see that people keep saying that Java is slow, but the runtime is actually a fantastic runtime. And I can create lots and lots of tasks. For example, in this particular test, I've created 200,000 of these. And I can create 500,000 on my old laptop without much of a problem here. Yeah.
Are you comparing to Erlang with the native code compilation?
Yeah. Erlang on Linux, on which it's best done, on an SMP box with hype enabled. Yeah. And likewise, I see far better results with compared to Haskell. You would think that Haskell should beat this outright, right? They have tail call optimization. They have no mutable stuff. In fact, they have no reason to be slower, but it runs circles around Haskell at this point. I mean, GHC -02 code. Anyway. So that's the task part. So the takeaways, I don't want to push the Erlang analogy too much because I have enormous respect for that runtime. But you can see that, it's a reasonable case to be made for very lightweight tasks. The second part is inter-task messaging. And that's a type system part, which I need to discuss. How do you make messaging safe? So the options are having immutable messages, you make copies, you can put a lock, but that's not really message passing. You can have fancy type systems, you can have linear type systems, ownership types, lots and lots of typing schemes to control, to deal with aliasing. And I have my own brand of sort of a pseudo-linear type system, which does put some constraints on on the shape of the message. Like I said, it's tree structured. And that essentially makes some of these things like ownership types, the reason they are so complex is because they have to deal with the generality of Java. And I decided to make a trade-off there and say that I'll put some constraint on what messages you can send, because to me they are philosophically different from messages, and I'll explain why. Mutable messages in Kilim are different. First of all, you have to implement a marker method called message, and messages can contain primitives, references to other message types, and arrays of these, and all immutable types like string and date and whatever else you might choose. The important thing, as I mentioned, is that ownership is passed linearly and no internal aliasing is allowed. And the other thing, which the philosophical difference, is that I encourage a non-encapsulated structure. Everything's out in the open. It's exactly, to me, as if it's equivalent in spirit to an on-the-wire representation or an XML format or JSON or whatever. If you have a message, it's open to be audited, logged, transformed, you name it, right? So it's different. And likewise, I think in your case, when you do MapReduce, all the structure that is actually sent, all the message that is sent is open, right? And that actually makes it so that allows things like scripting languages to be used as in the data flow without much of a problem. So I looked at your Google app product, and the interface is actually very, very simple and it can be completely encapsulated in a tree structured form. So going in and out of scripting languages does not have to be a pain, as long as you keep to this tree structured and open reflexive types. So how does one do this type system? It's a fairly simple thing. I associate capabilities with every node in a message tree. So at the very basic amount, you have the notion of modifiable. The tree is modifiable, the tree is unmodifiable, or the tree is unusable. Those are the three basic capabilities. And by modifiable, I mean that structurally modifiable, which means you cannot add to this tree, or this tree cannot be added to something else, right? You have to leave it as is. So the basic capabilities are whether it's modifiable or unmodifiable or unusable. I make a slight distinction in the modifiable case, a subclass, or not subclass, or some distinction, where I distinguish between the root of this message and the rest of them. The root is called free. So in some sense, I have 4 capabilities: free, cuttable, safe, and invalid. And that is the order, that's the lattice, if you will. Free says it's modifiable and it's a root of a tree. Cuttable says it is not the root of a tree, it's some intermediate node, but it's still modifiable, meaning I can modify its fields structurally. That means I can I can change its pointer valued fields. I don't care so much about whether you can change its primitive fields, right? I only care about the pointer valued fields, because that's what messes up all the aliasing is the big problem. So the fact that it is modifiable, unmodifiable, or unusable, these are all transitive properties. So all of it is modifiable, or all of it is unmodifiable, or all of it is unusable. So it's sort of like a deep const, deep invalid, whatever, right? So I'll concentrate on free and safe and invalid, I guess. So every node has these capabilities. And so the way you can modify structures is clearly through an assignment. You say x.f equals y, and you change the structures, right? So I'm going to look at 2 sets of rules. One is for assignment and one is for method calls. assignment, you say x dot f equals y. I have a node here. It's a node here that's referred to by a local variable x, and another tree here which is y. Clearly, in order to maintain the invariant that this particular node cannot have more than one incoming pointer, the right-hand side must be free. It must be the root. Because if it was already being pointed to by somebody else, I cannot have it on the right-hand side and assign it to somebody else. Right? So one of the things that the type system checks, the precondition is that the right-hand side is free. Right? And having done that, I need to change. Clearly, this is not free anymore. It's because it's being referred to this guy. It's still modifiable, but it's not free anymore because it's no longer the root. So I need to change its capability to cuttable. So it downgrades it. So essentially, from being free, it's now attached to another structure. The local variable changes capability. So there's a precondition and there's a postcondition, and the post action sort of changes the appropriate capabilities. And if there is a third variable, say z, that was aliased, y and z were the same thing, both capabilities, both y and z's capabilities would be changed. So the flow analysis, the static analysis takes care of all of that stuff. This is slightly different from your typical type system because each type is changing with the assignment. With normal type systems, they are flow insensitive. This is a flow sensitive type system. So, yeah.
Does it really need to be this complicated? I guess my question is, would it be easier to introduce since you're basically changing the language anyway, right? Could you introduce the notion of a first-class object called a message that just doesn't have pointers?
The question is, can you? Does it really need to be this? Yeah. So does it really need to be this complicated? Can you have a first-class message type that doesn't have pointers? And people have done it. They have value types, right? You don't have to, but I wanted to make it work with existing tools, existing messages, existing memes.
But the thing about it, it doesn't really work with existing messages because your messages have these given properties, right? You can't just say implement message. You can't just add that to an arbitrary type because there might already be a circular pointer or something like that.
Right. So the point is well taken that there's no existing type that already is a message. So what am I what am I catering for? So I guess I'm more catering to the existing mindset of dealing with pointers, having pointers, right? And it just makes my life easier to do that. And plus, it gets me a PhD. So.
That is not that.
No, I'm not. I'm just kidding. No, but I mean, it's true in the sense that if you have to retrofit it onto something like C++, right? You need pointers. So there are, for example, XMOS is a chip company that I'm talking to right now that has a language called XC that does not have pointers. It is C, but without pointers, it feels like a very different language. So if you are a dyed-in-the-wool C++ Java programmer, it's one thing to have a different type system altogether, or to incorporate pointers that you already know and love, right? So the point is that, like for example, in this case, you have a pointer to an array. It's fairly straightforward. Even if you're a C programmer, you just you can do your beloved P++ and stuff.
So the issue is, I think, I probably shouldn't derail your talk. The issue is that when I do things like distribution, when I pass messages between nodes, I avoid built-in serialization mechanisms like the play, and actually Google has its own mechanisms for doing sort of, create a message that doesn't actually use Java types just because we know that it's such a pain in the neck to do it with pointers and things can go around in cycles and all these little problems. It's much easier just to sort of do it the other way.
Right. But, so what you're saying is that you already know what you're going to distribute, and so you write your exported types, the ones that are going to go on the wire in a particular way, so that they are good for serialization. But the point is that I am catering to both concurrent or local solutions and remote. And as a writer of a particular task, I do not want to worry yet when I'm writing. I don't want to a priori decide whether it's going to be remote, local, or in a different language.
And I think that's fine. I would say that you use the same value type.
Yeah. So no,
I would say you use the same for both.
So
But, yeah.
point well taken, value types are there. Yeah, it's a different solution.
Yeah.
And work has been done on that. So I've gone with pointers because you can do things with pointers in languages like Java and C++ where it's just more convenient, right? Because the idioms are sort of well known. So how do I get these capabilities assigned to all these nodes in the first place? So I have an event class, and let's say I have a foo method which says, annotated, the same capabilities have free and safe. So essentially, I'm being told that foo knows that this parameter is going to be free. Whatever argument is going to be supplied is going to be free. And anything that is being supplied here is guaranteed to be safe. So that's the interface contract. Foo says that I promise to treat message as safe, and I promise to treat EV as free. Essentially, what foo is telling its caller is that I can do what I want to do, whatever I want to do, I can do with EV. And I promise not to touch message. I don't promise not to leak it. I promise not to structurally modify it. That's all. So to begin with, these are the capabilities I know of. And a flow analysis will basically tell me everything about the particular thing. So here, P equals new event. I have a new object, which is P, and it is free because it is a new object. Nobody else is pointing to it. And then I say message.a equals P. Clearly, this is a compile time error because message is safe. It had better not be modified. So it cannot be on the left-hand side, right? I cannot structurally modify it. ev.a equals P. That's fine. So now it has set up this link saying P is now hanging off of EV. It has also made sure that P is no longer free because it's now being pointed to by somebody else. And this is an attempt. The next one is an attempt to use something that's not free, no longer the root on the right-hand side. So clearly, that's an error. And the last one says an attempt to use message, which is considered safe. I cannot export it. I cannot alias it. I cannot leak it through some other channel. And so this is a compile time error. So essentially, given these two annotations and something like new, I can infer through all the control flow all the nodes that matter.
So you didn't, so say, to avoid having to do any sort of inter-procedural analysis, you just said safe means you can't assign that to.
Yeah, so I don't want to do inter-procedural analysis because inter-procedural analysis also means whole program analysis.
Oh, yeah.
Right? So I want to avoid that. So it is intra-procedural.
Well, so my point is that safe is very restricted, and that's fine. I think
That's
the
right.
thing out.
So safe is deep const.
Yeah.
So that was about how to infer capabilities. And this is the second part. So one set of rules we have seen for assignment, and the other thing is for method calls. So in this case, until this point, it says q equals p.f. So that's the image I have, p and q hanging off of p. And print q, that's fine because print says I'm not going to touch it. It's going to be safe. Don't worry. So that's fine to call print. mb.put q, mailbox.put says I'm trying to send it, but it's no longer the root, so I can't send it. Okay. So it needs, as it so happens, the signature says it needs a free thing, untethered completely. Nobody else should be pointing to it, and you better let go of everything. So mb.put q is a compile time error. mb.put p is fine because p is the root of the tree. That's fine. You can send it. It's not safe. It's not marked safe, so no problem. You can send it. But as soon as you have sent it, it loses visibility. The caller loses visibility, which means that anything that's hanging off of P is considered invalid. So at this point, if I attempt to use P, this will be a compile time error saying it's invalid. So essentially, you've given away P and anything that it points to. And you do a conservative analysis to figure out what it potentially could be pointing to. That's your rule for method calls. So essentially, the rule for method calls is fairly simple. You only supply, it must at least have as much capability as the target is demanding. And if the target says, if the target argument says that it's going to be free, then you better let go of everything that pointer points to. Okay? So all this sounds fairly complex, but you don't really think about all these mechanisms. It's sort of like, the VM does a fairly decent static analysis for null pointers or something that's not been assigned yet, But you don't think about it. It just says, oh, it says not assigned yet, then you go and assign it. You don't think about all the mechanics of it. So in practice, you don't need to know most of the stuff, right? You just need to know what the stuff is. I'll skip the cut operator. Cut basically says it gives you the capability to snip an edge. So a little bit about the static analysis here. I do something called shape analysis. And of all the heap analysis methods I've seen, shape analysis comes closest to my problem, where I can create an abstract view of the heap. Like in this case, what is hanging off of what? Right? Q is hanging off of P and stuff like that. Image, you have an abstract graph that you need to build up for every point, saying who's related to whom, so that if one pointer is sent and I want to invalidate something else, the other variables that might be related, I need to have a conservative but as precise as possible understanding of what else might be hanging off of this, so that you don't inadvertently use something that you're not meant to use, right? That could potentially be hanging off of the pointer that you sent. So I do the shape analysis. And if you notice, this original notion of transfer of ownership between the tasks has been converted to a different problem of transfer of ownership between methods. So instead of saying sending from one task to another, the problem has become sending from one caller to callee. And if the callee just happens to be doing stuff with kernel threads, that's the callee's business. Because if it says free, your job is to supply it a free pointer, and after that it can do whatever it wants, including not send it to another thread, but that's its prerogative. Which is why, with this type of system, you can essentially roll your own primitives like futures or whatever, and not have to worry about mailboxes being built in. So to summarize, Kilim has these lightweight tasks with automatic stack management and failure and state isolation. The negative part is that it's cooperative tasking, which is the thing I like about Erlang, because it's preemptive. Lightweight threads and preemptive. That would be nice, but with the VM, I don't have control over the VM. For messaging, it is fast, it's safe. The receiver can clearly reorder requests because after all, it's a buffer that it's receiving from. There is flow control. Mailboxes are flow control. And open structures are good for, you can, essentially it's nice for putting probes in there and doing filtering and transforming the message and stuff like that. And open structures really help. You can say that the downside is tree-shaped structures, but it's really not a problem in practice. And also, it's the case only when it's mutable. If it's immutable, then I don't care what shape it is. As far as ease of use is concerned, it's a uniform syntax. So if you dump something into a mailbox and you lose all ownership of it, if it just so happens that that mailbox is connected to a queuing system, that's its prerogative. So the view of there's no distinction really between distributed and concurrent programs. There are failure modes that might be different, but at least the mindset is the same. It's just message passing. It's easy to monitor because essentially the view of a task is, the external view of a task is essentially what goes in and comes out through mailboxes. And so you can put probes there. So you can view it like a hardware thing. You can put probes on the pins. And it coexists nicely with existing classes. And so I'll leave you to read the paper about how it does the coexistence. The downside, I would say, is that you have to a priori decide what the granularity of the task is. And that's a problem with threads, with processes, whatever. The only place where this stuff has been solved is, I guess, embarrassingly parallel programs where you can do, the compiler can figure out whether the computation in a particular array can be done in parallel and stuff like that. But in typical, non-mathematical tasks, I don't have an idea of how to solve it anyway. And I don't know of any other solution that does it anyway. So that's about it. The few references here about shape analysis, about one of the seminal papers called alias burying. And this is a paper that I'm going to be presenting at eCoop this next month. So that's it. So if you have any questions, I'd be happy to take it now or offline. All right. Thank you very much for coming.